Hello and welcome. I'm Pravir, and this session is a quaternary interpretation of quantum dynamics, QIQD Dialogic Computer. The way that this session is structured is I'll first briefly introduce QIQD. I'll then introduce dialogic computation. I'll run us through a representative application in terms of an algorithm to create a room temperature superconductor on the dialogic computer, and then summarize with thoughts around law-embedded quantum computation. So let's get to the essence of QIQD. QIQD is an interpretation of quantum dynamics based on existing structures that we see at the level of matter and life. The idea is that if we reverse extrapolate, looking at the level of life first, so this is a depiction of a cell, and in the cell we have four molecular plans, and any living cell has four molecular plans that we call polysaccharides, lipids, proteins, and nucleic acids. And these can be denominated in terms of some core functionality that in QIQD we call presence, power, knowledge, harmony. Now, when we go back a level of granularity to the molecules and the atoms that make up the molecules, then we find that the periodic table also is structured into four categories. We have S shell, P shell, D shell, and F shell atoms that also can be denominated in terms of the same four-tuple functionality, presence, power, knowledge, harmony. When we go back another level of granularity into quantum particles, we have the standard model, which also is categorized into four categories. We have leptons, quarks, bosons, and the Higgs boson. And we can also denominate these in terms of the same four-tuple functionality. The point being is that when we reverse extrapolate, then the hypothesis is that there's a fractal pattern, which is the four-tuple presence, power, knowledge, harmony, that shows up, or rather that's a root pattern that shows up as different fractals at different levels of matter and life. And that's the essence of QIQD. The point of it is that we can then arbitrate or intervene at levels of sophistication due to this QIQD dynamic or fractal pattern that animates even, for example, structures at the level of life or matter. So QIQD has been formalized in the book Pioneering New Avenues in Quantum Technology that came out just a few months ago. And it basically discusses the re-evaluation of quantum mechanics, or rather quantum dynamics, from a function-based deterministic perspective. And further, it goes into the alternative technology, the hardware, the logic, the math that would drive such a computer. Now, with the enhancements of LLMs, large language models, it becomes possible to train a large language model to think and to see the world from the point of view of QIQD. And so basically that's what I did over the last few months, was create a QIQD dialogic computation as an LLM-based embodiment of the quaternary interpretation of quantum dynamics. So in this interpretation, QIQD theory asserts that quantum dynamics is structural, fractal, and governed by qualified determinism. As I shared, it's qualified determinism because every object that arises, whether in matter or life, can be stipulated by a unique equation that gets its structure from this four-tuple arrangement of presence, power, knowledge, harmony. So we move beyond mere probabilistic approach to quantum in this point of view. The dialogic computation puts the theory into practice by treating computation as a lawful dialogue between core structures of QIQD, the hardware, and the math. So in the process of training the LLM, basically the end result of what surfaced was a law suite. So there's about 23 different laws that govern all computation. And these are symbolic mappings of key principles and equations that exist in QIQD. And then also there's a verb structure or a command structure, which has commands such as seed compose that composes a unique seed that would create a specific kind of energetic imprint. The architecture of the dialogic computer is basically slave master oriented. So we have the slave that translates human or natural language intent into lawful JSON operations. And then we have the master, which is the engine, which enforces laws, mutates states, and returns auditable summaries based on the law suite. And together, these ensure that computation is constrained, auditable, reproducible, and hardware aware. The hardware becomes the arena of the dialogue, and the algorithms becomes the dialogue flow. So now let's just ground this by looking at an algorithm for room temperature superconducting. And the idea is that a QIQD computer operates at the level of these imprints or functionality. So what does that mean? So for example, if you want to create a room temperature superconductor, we would want to have properties such as phonon modes, electron pairing strength, magnetic field interactions, lattice stability parameters. And these typically we may find in specific elements, but it may be very difficult to chemically combine these elements. But if we operate at the level of energetic imprints, which is what the hardware in QIQD is blueprinted to do, because the way that the hardware is structured is that it isolates the energetic imprint, which the subsequent computation then takes place in terms of the energetic imprint rather than the chemical properties of the element. So in the room temperature superconductor algorithm, which would create as an output the energetic imprint for room temperature superconducting in the hardware itself that would then be removable, we have as a first step something that we call seed encoding, and that would seed one or two properties that are required to begin with. Then you would have a dynamic interaction of properties through another piece of hardware called Mars. And then you would have the emergent property generation that would be governed by the Hamiltonian. And then you have the dynamic adjustment of the Hamiltonian to modify the overall system configuration to optimize interactions and coherence. And then you would have coherence management across different layers of these energetic imprints. Associated with each piece of hardware, there's a precise mathematical equation that is a QIQD-based equation. And when we when we train the dialogic computer, the LLM-based embodiment of the QIQD computer, then there's a mapping from these numerical equations to basically symbolism. So numerical to symbolic mapping. And so, for example, if we have a time-dependent Hamiltonian in one of the equations, then the LLM has to figure out what that means. And so the AHC, or adaptive Hamiltonian controller, adapts the system's energy landscape dynamically, and it creates the right command structure or verbs that can then be pieced together in an algorithm to emulate that equation, if you will, in coordination with other such commands. And that's how it works. So when I fed, for example, a system, as I showed you, of the 5 equations to create a lawful room temperature superconductor, then the LLM came up with a different algorithm, which it symbolically mapped, in which the steps were as follows. We had a seed compose that introduces a specific imprint into the hardware. Then you've got EM phase, EM split, and AT bind commands that probe spectral overlaps between the two channels of K and PER that have to do with phonon modes and the electron binding. And then you've got couple and entangle commands that establish order. So they basically reinforce the superconducting property that we're after. And then you've got beam mesh that actually checks the stability of the superconducting state. And what's interesting is that since this is a quantum process, we want to also gauge certain quantum metrics. For example, see the level of coherence, see the CH-SH margin to look at whether entanglement is happening within bounds so it doesn't get chaotic. We want to look at the level of entropy, commuting ratio, and so on. And at each computational tick, basically, these are assessed by the dialogic computer. And if anything's out of bounds, it will suggest corrections that need to be made to the algorithm or a new command that needs to be introduced. So what I shared here right now is the symbolic simulation where we run symbolic dialogic computation based on the interpreted law suites and verbs in an LLM. And this generates lawful blueprints. Its utility is in checking symbolically with whether certain kinds of algorithms may work in QIQD hardware. At some point, this would need to be transitioned into numerical embodiment of this computation on an HPC, a high-performance computer. There we envision that we'd need AI generative models to propose candidate structures of these imprints, for example. We'd need reinforcement learning to optimize the verbs and parameter sets. We would have to run parallel HPC solves so that many candidates would be created simultaneously. And then we would evaluate the structural KPIs that we isolated as being important. And then at some point, this would transition to hardware prototypes where we would build A-series qubits, stack fabric, property gates, which are key parts of the hardware that have been embodied in the QIQD Dialogic Computer. And this would finally lead to integrated QIQD GPU pilots where we can run full stack QIQD programs, not only in RTS or material kind of applications, but also cybersecurity and other applications as well. So to summarize, the idea is that we're reframing computation because QIQD replaces probabilistic qubits with seeds. The dialogic computer unites expression and enforcement through a constitutional law suite. And every tick is capacity checked, property neutral, and entropy validated, and governed by the other laws that are important in QIQD. There's demonstrated lawful propagation. For example, in the room-temperature superconductor case study, we had lawful coupling and bounded entanglement that resulted in increased coherence and other metrics that were above the necessary bounds. And we have a structural continuum from dialogic simulation to HPC numerical embodiment to physical hardware. And the important point is that it's all, even as we progress to the next stage, we won't let go of the previous one because there's utility in being able to use dialogic simulation to just check whether a candidate algorithm might be useful in that QIQD regime. As I said, there's broader implications. We could use the same process in cryptography, getting, for example, in the cyberquantum area, getting into structural assurance beyond probabilistic assurance. And then also, as this application is showed in the materials area, but also in other complex systems and AI applications that may benefit from such a dialogic lawfulness that involve multi-scales. Thank you.